Okay. Okay. Still appears to be working. Dejan, Doug, Trevor, Jaden, Caitlin, Jaden Hamilton, Zach, Yoakum is here, Tyler is here, Claire, Allie, Cade, Ben, Nathan, where is Caitlin and Josh? All right. Based off of the conversations, I think the vast majority of you are either done talking or not on task, so we will go through it. All right, Jaden Hamilton, what's the first step I do when I assess an equilibrium expression? Okay, so the first thing that I want to do is I want to identify what does not participate in equilibrium. So which two substance types do not participate in equilibrium? Turn and tell your table partner. What does not participate in an equilibrium expression? Yeah, and the heat. Good.
What do you mean not quite? That's exactly what it is. Oh, take it out.
And
Take it out. Oh, snap.
liquids and solids. All right. Here we go. Do not participate in equilibrium. There are three pretty good answers. One. Let's hear from Zach Shanks. Zach, what's one of them? A catalyst has nothing to do with equilibrium.
So would that be heat?
No, not heat. Like a platinum catalyst or a metal cathode that was added. Okay? So heat would be one of them. Changing temperature is one of the ways we can shift it. All right, a catalyst does not participate. Sierra, what's another one? If it's a solid, it is no longer in solution and is the most concentrated form it can be. It does not participate. And Trevor, what's the last one? Molecules. Very good. Molecules, specifically in the liquid form, do not participate in equilibrium. And so the very first thing I do is I cross them out. Dejan. I know, this is perfect. I didn't include catalyst, but it's absolutely true. So in this case, I look. Heat is included. Gas, 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 liquid. All right. I cross this out. The next thing that I do when I am assessing an equilibrium expression is I count how many gas particles, relative gas particles, do I have on both sides of the equilibrium expression. So Bailey, how many gas particles are on the left? It'd be 9. Good. 4 and 5 would give me 9 relative gas particles. On the right, how many do I have, Bailey? 4. Very good, because the 6 waters don't count. Okay? So now if we keep those things in mind, we're going to go through and we're going to ask what happens if. Taking into account, if I add something, it shifts away. If I take something away, it shifts towards. And if we talk about gas particles, we think about dogs and yards. The larger the volume, the more gas particles will exist. That's the side of equilibrium that will be favored. The smaller the yard, the fewer the dogs. The smaller the volume, the more reactions that will take, and the side that has fewer gas particles will be the one that is favored, and we shift that direction. So Cade, let's look at number 1. If pressure increases, what happens to volume? And if volume decreases, which side is favored? Shifts right. If we shift to the right, what will happen to the concentration of NO? Claire? It increases. Very good. Number 3. Which direction will equilibrium shift if I add oxygen? Sierra. Add oxygen, shift. Sorry, what did you say? To the right. Thank you. If I shift to the right, Mr. Cabela, what happens to the concentration of NO?
The concentration will
It'll increase because I'm making it. If I add heat, Ben, if I add heat, what will happen?
You add heat. No, go right.
To the right, what will happen to the concentration of NO, Ben? It will increase because I'm making it. If I increase the volume of the container, Michaela, what happens? It will shift to the left. Very good. Larger yard, more dogs. If it shifts to the left, what happens to the concentration of NO? Nathan.
I thought it would decrease.
It will decrease. Very good, because it's now a reactant. I'm using it up. If I remove water from the equation, Dacian, if I remove water, what will happen? Nothing. No shift. Miss Fisher, that wasn't an option. Fair enough. It should have been. It should have been for all of them. What will happen to the concentration of NO if there is no shift? Allie, what happens? No change. Mic drop. We rock at predicting equilibrium shift. All right. Take your quiz out. This is what it looks like. That half sheet on your own. Please indicate the shift, left, right, or no change. And for the change in H2 concentration, circle which is the most appropriate answer. make sure that you pay attention to the fact that the concentration is always asking about what happens to hydrogen. Okay.
No, it says E.
Oh, now. When it says E,
The Wi-Fi
now
is
it's a little
unplugged.
flashing. Oh, now it
So
says
do we
E.
need to go back up there?
That's okay. I'll grab that.
Yeah, mine just says.
All right,
Oh,
when you're
now
done,
it says-
go ahead and just flip it over. Don't worry about your menus. They got unplugged, and so they need to all be reset. So I'll just grade it by hand. As soon as you enter anything, it's going to reset. Or it's not going to respond. All right, Mr. Cabela, please put that down.
How many points is it gonna be?
You have a moment longer. Just take. I have to check something.
Are we going over it together
All right. Thank you, my dear. All right. Yeah, Doug, I don't know why those weren't in there.
What?
I don't know why that wasn't in there. Fixed. Thank you. Not even going to humor that question with a response. All right. Okay, here we go. Let's check this out. So this equation felt awkward because it was slightly different than ones we've looked at before. Just like how if I gave you a quiz and had all the answers be A, even though you may feel very confident you were correct, you might still feel uncomfortable because they were all A's. Agreed? So there are times when we are facing situations like that. All right, so that's the first thing we do is we cross out things that are not included in equilibrium. Solid, not included. Gas, yes. Energy, yes. Liquid, not included. Gas, yes. I have one particle of gas on the left. I have one particle of gas on the right. Dejan.
Because the heat is so hot that it melts.
Heat is always included, and we say that substances that are liquids are as concentrated as they can be, therefore they are not participating in equilibrium, which means molecules, liquids, and solids are not included. So that's step one, right? We look at states of matter and we take anything out that can't be included in equilibrium. Now I'm looking, I've got one gas particle, one gas particle. The first question talks about decrease in volume. I have one and I have one. There is no difference between these two. It doesn't matter what happens to the volume. There's no one side that's different than the other. Agreed? There can be no shift if there's no side that is favored. No shift, no change. If I add copper, is copper included in equilibrium? No, no shift, no change. If I remove water vapor, well, here's water vapor. If I remove it, I'm taking it away. If I take it away, I shift toward the sides. So I shift this way. I recall that we're talking about hydrogen concentration. That means hydrogen will decrease because it's shifting this way, and I'm using hydrogen up. If I decrease the copper oxide in the equilibrium, is copper oxide in equilibrium? So no shift, no change. If I cool the reaction by removing heat energy, I take away. Take away, shift towards the side, and hydrogen is on this side, and I increase. Allie.
So
I missed every
I forgot to put the numbers above it. Would you count that wrong?
No, but you'll be more likely to make a mistake if you don't do it.
Okay.
Okay. Yes, Mr. Yoka.
So even if a molecule is a gas,
As long as it's a gas, it's in equilibrium.
what a data.
Because like O2 is a molecule, and N2 is a molecule, and H2 are molecules, but they're gases, and so therefore they're homogeneous and in solution and can be concentrated. So this goes in as a practice test, a little practice quiz, right? I record, this is where we are. We do this again tomorrow. When's the next one?
Tomorrow.
Right? So practice is going to make more confidence, right? So making sure that you're trying these on your own, going over ones we've done before and checking if you understand why they are what they are. Tyler.
I guess I don't understand number 8. Like if you're moving water, which is H2O, why would it shift? Why would it not shift? Because it goes decreases, it shifts towards.
So it's going to shift to replace what I did. Equilibrium will always attempt to reestablish itself. If I remove something from equilibrium, the equilibrium will shift to replace what I took away. So that's why when I take something away, it shifts to replace it. And when I add something, it shifts away to use it up. So you'll see these go in. It'll be out of 10 points. We'll see where you're at. And then we do another one tomorrow. When's the next one?
Tomorrow.
And the test over Unit 12 is on Wednesday. All right. So let's take out your packet for me, please. Packet. Take out your packet. Let's review a couple of important dates for where we are and where we are going. Okay, here's our packet. On your desk, you need your packet and you need a calculator. Packet and a calculator. First up, Wednesday, May 16th, Unit 12 test. Monday, May 21st, final. Now, Mrs. Larson and I go back and forth on this quite a bit, and the concern is that if I give you your final on Friday, I'm not giving you enough time to prepare. So right? If I give you your final on Monday, I can make the argument as an instructor that I have provided you additional time. Now, whether you choose to use it or not is up to you. I'm providing you the opportunity to do so. I would always like to err on the side of giving you the opportunity to prepare. Now, having said that, I also know that it's Monday. And you can argue that, oh, I don't like tests on Mondays. Well, me too, except life happens. It's called life. You're going to have projects due on Monday. You're going to have finals due on Monday. You're going to have tests that you have to take at night. Like, that's just the way it's going to go. When you have finals in college, you may have a class on Monday, Wednesday, Friday from 10 until 11, but then you will be assigned a final testing time. It will not necessarily be during your regularly scheduled time. You may have your final on Tuesday at 4 o'clock in the afternoon because that's when the chemistry department decided that's when you're taking your final. It is up to you to be prepared. When you come in on Monday, you will sit down, your final will be on your table, you'll pick up your Mimeo vote, and you will start. There will be no conversation time, there will be no reviewing time, and you're going to want every one of those 87 minutes to take your time. Okay, so if you have questions, the time to be asking them will be today after school, tomorrow after school, Wednesday after school. Right, this week is time to be asking questions. I won't be answering any questions on your actual final day because you'll need all of that time for the test. Okay? Questions about the Unit 12 assessment on Wednesday or the final on Monday?
What are we gonna do Tuesday? Just watch a movie?
Tuesday, we're making s'mores and checking the textbooks and.
Woo!
Yep. Okay. Also, again, on missing work is due on Friday, on or before Friday the 18th. All right. You will be handing in your packet to me on Wednesday as well. Make sure that you are finishing your vocabulary and doing your assigned reading. We've covered everything with the exception of Learning Objectives 6 and Learning Objectives 9. And those go back to this idea of models, chemical models, what they tell us, what they don't tell us. So let's flip in your packet to equilibrium. See, I'm on equilibrium chapter 18, and then I'm flipping to the back page. All about chemical models. Chemical models, scientific ones, help explain systems that are complicated, that I want to simplify, like an ecosystem. It can explain systems that are very large, that I have a hard time visualizing, or very small, like atoms. And they can also explain things that I can't necessarily see, like chemical reactions. They're going to be really good at one thing and maybe not as good at others. This is the chemical model of a chemical equation. It tells me the reactants that are part of this reaction, potential products that can form. It doesn't tell me how it happens. It doesn't tell me how long it takes. And we've kind of polished this model because we've got arrows going in both directions. So now we're saying, hey, heads up, like this reaction can form products and those products can reform into the reactants. So for this first example, we have acetic acid in water. So acetic acid is the chemical in vinegar. Okay? So acetic acid is in the family called weak acids, meaning that it doesn't actually want to dissociate into acetate ion and hydrogen. It wants to stay stuck together as acetic acid. So the reaction only will dissociate 4%. So if you have acetic acid or vinegar, you don't have lots of hydrogens and acetate ions. You mostly have acetic acid stuck together, right? So this reaction is trying to show you that because the model of the arrow is very small in the forward direction, and we're trying to communicate that very little of it goes this way. The vast majority of this reaction favors this side, sticking over here with acetic acid and water. So the reaction is only 4% complete in the forward direction in equilibrium. Whereas, now, and I can shift this, like Le Chatelier told me, I can shift this by changing concentrations, or by changing volume, or perhaps by changing temperature. I can shift equilibrium. Whereas this reaction, hydrogen gas and iodine, will form hydrogen iodide. We see that it's 78.2% complete at equilibrium. So almost all of it goes this direction, making hydrogen iodide, and very little of it, like what, 12%, wants to stay, no, 22%, wants to stay over here as the reactants. So there are at equilibrium, we're trying to polish this model so that when we say it can go both directions, you know what that means, like how much of it is going to go one direction. So we need to have a different model that can tell us the how much question. So Le Chatelier said that there are 3 ways we can influence this or this, the forward and backward direction. So I'm going to grab my highlighter. We're going to highlight as we go because these are just some reviewing and content notes. The first factor that we can use to change equilibrium would be concentration. Concentration is affected by changes only in solutions and gases. Pure solids and liquids are as concentrated as they can be, no matter what their mass, so changing their amount will not shift equilibrium, which is why we would leave copper liquid out of equilibrium, even though it's not a molecule. So if I look at my pretend equation, A, B, C, and D, let's ask Tyler. Tyler, will A participate in equilibrium? How about B? It's in solution. So, yes. How about C? How about D? No, because it's a solid. All right. So my first step I would do is I would cross it out saying not in equilibrium. It's crystallizing and falling to the bottom. All right, Mr. Cabela. Fake it till you make it. Sit up, lean forward, grab a pencil, highlight with us. If I increase the concentration of A or the concentration of B, what direction will equilibrium shift? To the right. What if, let's ask Ryan, what if I decrease concentration of C? What direction will we shift? To the right. Good. Decrease, take away, shift towards. What if I decrease the amount of D? Mr. Yoakum?
It would not shift at all.
Very good. No shift because it is not part of the equilibrium expression. All right. So that's concentration. The second way that Le Chatelier identified we could shift equilibrium was through changing the pressure and the volume. But we recognized that this only affects gas molecules, that liquids and solids essentially cannot be compressed enough for us to change their concentration. So if I look at the equilibrium expression that's provided, Doug, will A participate in equilibrium? No, because it's a liquid. How about B? And how about C? Perfect. All right, if we look at how many of each of these we have, Ben, how many gas particles on the left? 1. Very good. We assume that there's a 1 in front of this. And how many gas particles on the right, Ben?
2.
All right. So I've got a coefficient 1 that we assume is here, and I have a coefficient 2 for my 2 relative gas particles. All right, let's look at what happens to equilibrium if we do the following. All right, let's add Cade. If I increase pressure, what happens to volume? Decrease volume. If I decrease volume, which direction will equilibrium shift? To the left. To the side. Okay, so like what's happening? I decrease volume, I have more collisions, therefore I will have fewer gas particles because they will have collided and reacted. I will shift to the side that has fewer gas particles. Thumbs up if you're with me. Collision model. That's the theory. If you just want to use the acronym, smaller yard, smaller dogs, right? Smaller yard, fewer dogs. Decrease volume, I shift to the side with fewer dogs or gas particles. All right, if I increase the volume, Allie, which way will we shift? To the right. If I increase volume, there will be fewer collisions. If there are fewer collisions, I will end up having more gas particles. If the same number of gases are on both sides, then we experience no shift because there's no difference. There's no preference. They're the same. All right. Concentration, pressure, volume. Last is changing temperature. If temperature is increased, equilibrium will shift away from heat formation, whatever side heat is on. If temperature is decreased, it will shift towards the side. So here we have heat as a reactant, it is endothermic. And here we have heat as a product. It is exothermic. Heat is coming out of the reaction. All right, Miss Michaela. If there is a rise in temperature, I am adding heat. Add, shift, away. So for number 1, I add heat. What direction will we shift? To the right. For number 2, a rise in temperature will shift equilibrium which way in number 2? If I add heat, Bailey, which way will we shift? Add, shift, away. So we're going to shift to the left. Add, shift, away. So this is just a review, right? 3 different ways that we can influence equilibrium: changing concentration, changing pressure, changing temperature. Okay.
So when something is no shift, then it is at equilibrium.
Correct.
Okay.
That whatever change we made will not change equilibrium. It's just going to keep doing its thing.
Okay.
All right. Flip to the next page, please. 1 through 7. 7 different equilibria are provided for you. Step 1. What's the first thing we do before we try and solve the problem? Sierra, what do we do? All right. Perfect. We identify what is included in equilibrium. After we do that, then Nathan, we identify what? We count the number of gas particles if gases are included. If there are no gas particles on one side, then we say there are 0 gas particles on this side. Okay? And then predict the shift. All right. 1 through 7. Okay, so you guys put your work on the board, and we're going to walk through the logic. So the first thing I do is I'm going to try not to move the paper too much so you can still see the answers. All right. So I have 2 gas particles and 1 gas particle. If pressure is decreased, volume increases, and I have a bigger yard, and I have more dogs, and I shift to the left. Gas participates, liquid does not. I have 2 gas particles and 0 gas particles. If pressure is increased, volume decreases, and I shift to the right. Smaller yard, fewer dogs. I have 0 gas particles here and 2 gas particles here. All right. So this is liquid, so there's not participating 0 gas particles.
But I had the arrow, and then you told me since it was liquid, there was no shift.
If it was a liquid, it would be no gas particles. And then I think I told you to write down how many gas particles there were on top of each one of them as a reminder. All right. 32, and I totally could have made a mistake, and if I did, I very much apologize, because I'm human and that's possible. All right. Kilocalories is heat, right? So you might see the word heat, or you might see a measurement unit in heat. If heat is decreased, take away heat, I shift to replace, take away, shift towards, I shift to replace. Okay? If heat is increased, heat is on the right, I add, shift away, add, shift away, shift left. All right, liquid, no, aqueous, aqueous. All right, we have no gas particles, so I can't count gas particles. If chlorine is removed, chlorine, take away, shift towards. Take away, shift towards the side that it was taken away from. Dejan. That's okay. I mean, really, that probably tells me that the equilibrium is going to go way to the right. All right, if water, all right, solid, no, gas. All right, if additional water is added, add, shift to the right. Okay, I've got a volume question. So I've got gas, and a liquid. I have 0 gas particles on, oh, can you guys see that? I have 0 gas particles on the right. I have 2 gas particles on the left. If I increase the volume, I have a larger yard. I will shift to the left because fewer gas particles will react, more gas particles will remain, or larger yard, more dogs. How did we do? Not horrible. All right. Questions? Questions? Identify what can't participate. Solids and liquids. Count gas particles. Right? Think about heat. Add, shift away, take away, shift towards. Volume, smaller yard, fewer dogs. All right, flip. We're going to continue polishing our idea of what this means to be reversible. All right. So two French chemists, bless their hearts, discovered in 1862 that for an equilibrium system, the ratio of the product concentrations, math words. Product also means what in math?
Answer to a multiplication.
Multiplication. All right. So think of this. This is multiply. If I multiply the product concentration and I relate it to the, right? So here, if I multiply the reactant concentrations, I get this value of how they're related. All right. Here's the key. I have no idea what a reaction will do until I do the reaction. So where equilibrium exists can only be determined through careful experimentation. And through experimentation, I'm going to measure how much I added and the concentration of what remains. And then from there, I look for a pattern. And one of the best ways to look for patterns and trends in data is to graph it. So what we would do is we would do an experiment. We would graph what I am changing and what I'm measuring. So what I change goes on the X. I am changing the concentration of the products. I'm measuring the concentration, or time out. Ugh. I'm measuring the concentration of the reactants. That's what I'm adding, right? And then I'm going to observe the concentration of the products that form. And then I'm going to graph it. And I'm going to get some relationship, right? As I add more reactant, theoretically, I'm going to get more products. Thumbs up if you're with me. And when I do this, I say, what's the pattern? So I would go to my Excel program. I say, what's the pattern? And what would I do as a mathematician? What would I tell Excel to do? Graph it and look for the
Pattern.
I would say find the best fit equation, right? Find the best fit line. And that would give me an equation. And if I wanted to say, how does this change? I would look at the slope of the line. Okay? The slope of the line tells me the relationship between these products and the reactants. Slope is change in Y over change in X. Y are the products. X are the reactants. And K is the slope. So K is the relationship between products and reactants. And we give it a fancy name in chemistry because we're looking at equilibrium. So we call K the equilibrium constant. And we've already seen this before because we said equilibrium constant of water, Kw. And we said that Kw equals the concentration of hydrogens times the concentration of hydroxide, and it was this number, 1 times 10 to the negative 14th. Thumbs up if you remember this from last unit. Okay, we said, hey, this is the equilibrium constant. It's how much water will dissociate and break apart, because water could do this. Liquid water could become H plus and OH minus. Now, why did we not include water in this equation? Tell your table partner. Why is water not in the KW expression? It's not in
Solution.
Thank you. Okay. Why? Hello. You're either like, this is so like I got it, or you're like, what the heck, Fisher? Okay. Why did we not? So Trevor, why are we not including water in this KW expression? Because it's a molecule and it's not in equilibrium if it's a molecule. So when I make my KW equation, I put the products, well that would be hydrogen and hydroxide, and I would put the reactants on the bottom, but there are no reactants. So it's over 1, and we just ignore it altogether. Okay? And that tells me how much of this molecule will dissociate. Now, KW is 1 times 10 to the negative 14th, which means that the number is really small. So the amount of water that's actually dissociating is a very, very small amount of water. Most of it is stuck together as water molecules, but some of it has dissociated. KW tells us how much of it has dissociated into products and how much of it remains as reactants. Okay? So we're going to practice identifying what should be in the KW or K equilibrium expression. We're going to practice calculating it from lab data. Like, again, I can't find this any way but to give you concentration values. We'll say, at equilibrium, these are the concentration values. What's K? And we'll find, and then we'll ask the question of, okay, if that's what the K value is, which direction is this reaction really going? Is it going to form products or is it not to? Okay, now, if my job is just to take chemistry so that I can like check off a list on my resume to say, took chemistry, move on, it's enough just to say I get it. Reactions can dissociate and go backwards. That's totally fine. If my job is I'm going to become a PharmD and become a doctorate in a pharmacy, and I want to be a research pharmacist, then and I'm working for a chemical company, and the chemical company says we need you to synthesize this new pain pill, or you're being hired as a chemical engineer to streamline a process, I need to know what the reaction will do. And the K value tells me that. And I don't have to figure it out on my own. I can look it up. It's in books. It's online. I can say, what's the K value for hydrochloric acid? And it will tell me how much of it will dissociate and how much of it will remain. Or I can say, what's the K value for this reaction mechanism? And it'll tell me. Right? So in the old days, it was published in the Bible of chemistry. This.
Oh my yeah.
Right? The CRC of chem. And in here, it tells me all about all of the chemicals, their trade names, how they're manufactured, what they look like, and things like physical constants, melting point, boiling point, density, solubilities, and K values.
What is it organized under? Like the
Elements.
How do they organize things? Alphabetical.
By
And by family.
Sorry, I
All
couldn't
right.
get my question out on time.
Okay.
Thanks, Ben.
And you can just Google it. Like we would now, chemists don't necessarily need to look at a handbook of chemistry and physics, the CRC. We would Google it, and all of this information would be online. But your job is not going to be to find the K value; it's going to be to interpret what this means. Okay. All right. So let's look at an example. We're going to revisit this equation from earlier today. We have hydrogen gas and iodine forming 2 hydrogen iodide molecules. So the K value, this K constant, products go on top. I have hydrogen and hydrogen. Now we normally wouldn't write it like this. We'd write it like this, 2HI. Agreed? But that means I have 2 hydrogens, hydrogen plus hydrogen iodide plus hydrogen iodide. Okay, so if I put the products on top, I have hydrogen concentration times hydrogen concentration divided by the reactants on the bottom, H2 concentration and I2 concentration. I also see that this can just be written as HI squared, because there's two of them. Which means that the coefficient here is a power in the equation. Whatever the coefficient is from stoichiometry becomes the power in the equilibrium expression. So turn inside your table partner. The stoichiometric coefficient becomes what in the equilibrium expression?
Exponent.
Not the exponent power, not the
Say it again.
exponent. The power. Exponential. Alright.
Actually, I don't know.
What about this? What do you call an alligator wearing a vest? An investigator. Alright. Okay, let's look at the expression. Tyler, what do we do with the coefficients in front of the compounds? Turns into the power. So the generic formula, this is called the equilibrium expression. If I say write the equilibrium expression for a reaction, I expect you to write this. KEQ equals products raised to the appropriate power divided by reactants raised to the appropriate power. Okay? If there's no coefficient, there is no power. If there are no reactants in equilibrium because they're solids, then this becomes a 1 on the bottom. If there are no products because they're not in equilibrium, then the top becomes a 1. So let's look at a couple of important notes about K. K has no units. For our purposes, K has no units. It tells us the relationship between products formed and reactants remaining. K cannot be predicted. I can only determine K from lab data. K can also have other names. Don't be intimidated. Ka means equilibrium for acids. Kb means equilibrium for bases. Kw means equilibrium for water. All right, so the subscripts just tell us specific families, but it's just still equilibrium for K. If I change the temperature, Le Chatelier's principle tells me changing temperature shifts equilibrium. So I can only determine this data for specific temperatures, which is why the problems will say, here is concentration data at blah, blah, blah temperature. Just be like, oh, okay, that's it. We don't do anything with it, but we acknowledge that if we change temperature, that it would change KEQ. And then we recognize that solids and liquids are not in equilibrium and therefore cannot be written in the equilibrium expression. All right, 5 statements about what K is. I want you to grab your paper. Hold it up. Grab your paper. All right. You're going to touch 2 desks, and you're going to talk to someone that is not currently sitting by you and tell them how to write the equilibrium expression. Use your notes if you need to. Go. Stand up, touch 2 desks, find someone new.
Oh my god. Found it. Anyway, for like Mrs. Fisher,
Yeah.
if I know units, does it mean like grams or
Correct, like no label on it. Now, technically, however, for our purposes, okay, go ahead and finish up your conversation with your table partner
In the first couple days, yeah.
and have a seat.
I was really good at that.
Okay, all right. KEQ. Equilibrium constant. Michaela, tell me something about the equilibrium constant or the equilibrium expression.
The reactants are on the top and the products on the bottom.
The products are on the top and the reactants are on the
Yes.
bottom. I only mix them up all the time too when I'm saying this out loud. All right. So I see that my products are on the top, my reactants are on the bottom. Good. Allie, tell me something else.
The
The coefficients from the balanced equation turn into the exponents. Good.
I just have a question. So when you have the two arrows that are like, I mean, they seem equal length and equal size.
Mhm.
Why can the left not be a product?
It could. We have to choose a direction to describe the equation, and so we always describe KEQ based off of the equation as presented, reading left to right.
Okay, so if the left was a product, would it be A on top and B on top?
If we rewrote the equation as C plus D yields A plus B, we would have a different KEQ for that reaction.
Okay.
It's a very valid question. Like, why is it that we write it the way that we do? And the answer is we arbitrarily chose it that way. And KEQ will change if we change the direction that we write it. So always write KEQ for the reaction as given. All right. Hey, Tyler, you're the next pick. All right, Nathan, tell me something about KEQ. Yeah, products are on the top, reactants are on the bottom. Coefficient becomes the exponent. We write it as written. What else? Five statements on the board.
Oh, well, that's just right there.
There you go. Well, give me one of them.
Has no units.
All right, has no units. Bailey, what's another one? Can't be predicted. So I have to give you lab data, right? So this isn't going to be something where I'm going to look at it and figure it out. I'm going to give you data that you're going to use to solve a problem. You're either going to determine a concentration at equilibrium, or you're going to find out what equilibrium constant is. So let's try some, okay? Let's look to the next page. Calculate the K value for the given reaction. The K value for this reaction is given at 30 degrees Celsius, and these are the concentrations. Moles per liter is another way of saying what unit? Mr. Cabela, moles per liter is another way of saying molarity. Right. So I can either give this to you as 8.8 moles per liter, or I can tell you 8.8 molar, and they're the same thing. Don't get intimidated. Okay? All right, I have an equilibrium reaction that says 2 nitrogen monoxide plus oxygen gas makes 2 nitrogen dioxide. What's the first step when I look at an equilibrium expression? Miss Hamilton, what's the first thing I'm going to look at when I look at an equilibrium expression? Very good. I'm going to check to see if I have to cross anything out, liquids or solids. Are there any liquids or solids or catalysts to cross out? No. Okay, so everything is included. Okay, so the next thing I do is I write the equilibrium expression. I say, okay, KEQ equals, and products go on top. So I put concentration of NO2, brackets mean concentration, and the 2 becomes the power, divided by, now I go to the reactants. Everyone's writing this with me.
Should we leave the 2 down there with NO? Or do
This
we,
2?
Put just, yeah.
This
We
2
have
right
to
here,
keep it?
Ben?
Yeah.
Yes, because that's part of its name. NO2 is the formula. That's why the 2 has to stay with it.
Why is it different from like the ones up top? Because like
There's NO2 here,
yeah,
and
there's no-
NO2 here. There's NO here, and there's NO here. And then there's O2 and O2. So we have 3 different molecules that are very similar but different. Does that make sense? No? All right, I'll come and look at it in a second. All right, so I have the product NO2. So I write NO2, and it has a squared because there's the coefficient 2 becomes the squared. And these are the products. On the bottom, I write the reactants. I have nitrogen monoxide, 2 squared times oxygen, O2, with the coefficient of 1. And I don't write the 1 because we assume there's always a 1 there and it doesn't change the number. Okay, I'm given data and I recognize that KEQ does not have a label. So there's no reason that I'm going to make you put labels on numbers that don't get labels. So I write. Now I substitute in my numbers. I have NO2, 8.8 squared divided by NO, 1.2 squared times O2, 1.6 equals. And I do expect you to write out this information before you type it into your calculator. So grab our calculators. 8.8 squared divided by 1.2 squared times 1.6, parentheses. Okay, how many significant figures should I report with my answer? 2, because there's 2 in the number. So my KEQ value is 34. All right. What does that mean? Excellent question. This is the ratio between the products I made versus the amount of reactant that is left. If the number, if the K is greater than 1, then I have more product formed than reactant. If KEQ is greater than 1, then the reaction is going predominantly to the right. If K is less than 1, then more reactant is formed than product. And this is the arrow direction that's actually preferred. So if I were to polish this reaction with the KEQ of 34, what's really happening is nitrogen monoxide plus oxygen gas is mostly forming nitrogen dioxide with a little bit coming back. And I can draw those arrows in different sizes because KEQ tells me that the relationship is going this way. Yeah, so like what does it mean? That's what. And so if I'm a chemist and my job is to create a product and I have multiple reactions I could possibly use, I'm going to look for the reaction that has the greatest KEQ value if I want it to go to completion. Or if I want to stop something from happening, I want to find the smallest KEQ value so I can push it this way. And then I know Le Chatelier's principles tell me that I can shift it even more if I change concentration, temperature, or pressure. So I can push it even more one direction. All right, let's try a couple more. Let's look at number 1. So the first thing I do is I check, is there anything in this reaction that cannot participate in equilibrium? No, we're good. We've got aqueous, gas, gas. Okay, so the second thing I do is I write KEQ. KEQ equals, products go on top, PCl3 to the power of 1, well, don't care, times Cl2 to the power of 1, oh, good, divided by PCl5. And they want us to tell them the K value. So now I substitute in my concentration values, PCl3, 0.0247 by Cl2, 0.0247 divided by PCl5, 0.0096. I grab my calculator. How many significant figures should I be reporting in my answer?
4.
I've got 3, 3, and 2. So we'll report
I thought
2.
anything after a dot.
Anything after a non-zero, after a non-zero number. All right, 2 significant figures. So we report this to 2 sig figs. I get 0.064. KEQ is 0.064. KEQ is less than 1. Which means, what direction is this equilibrium favoring? Towards the reactants, to the left. I have more reactants than I have products, which is why this number is less than 1.
All of them are towards the reactants. No matter what, it's going to be towards the reactants.
No.
But how come it says it's greater than 1 towards the reactant and then it's this?
If the
Less
K
than-
is greater than 1, then more product is formed than reactant.
Yeah, I know, but then you have the arrow pointing towards the reactant.
Sorry, I meant like in the equation, like A plus B makes C plus D. It shifts to the right in the generic
Oh.
equation. Sorry, Ben. Thank you for saying something. I didn't mean to confuse you. I just meant like it shifts right. And if K is less than 1, then it's shifting left in that generic equation. All right, let's look at number 2. We're going to do 2 more, and then you're going to do the rest on your own. So if we look at number 2, does copper participate in reaction? No, so cross it out. How about silver ion? Yes. How about copper ion? How about silver solid? Okay, so we write KEQ. KEQ equals products. That's copper ion. No coefficient, so it's nothing. And then we got silver ion with a coefficient of 2. So what do we do with that 2?
It becomes an exponent.
Comes the exponent. All right. KEQ equals copper, 1.6 molar, divided by silver, 1.1 molar squared. Silver squared. How many significant figures will we report? 2. 1.6 divided by 1.1 squared. I want 2 significant figures. I get 1.3 and a whole bunch of calculator junk. KEQ is 1.3. If we said what direction is being favored, towards the product. This is not by much, but it's still the direction it's favoring to the product, whereas this one was favoring to the reactant. All right, we're going to look at one more, but in order to find this one, you have to flip your paper to the next side. And I want to look at number 9. All right. All of them up until now. So again, if there are no species in solution to participate, you just put a 1. Okay, so if there's no products that can participate in equilibrium, you put a 1. And if there are no reactants that can participate, you just put a 1. Right? But we don't always want to know what the equilibrium constant is. Sometimes we want to know if this is the equilibrium constant, how much will I make or how much will remain. So number 9 is a how much will remain question. And it's asking how much hydrogen and chlorine will remain if K is 1.8 times 10 to the 33rd and the concentration of HCl at equilibrium is 14.5 molar. So I don't know what H and Cl, H2 and Cl are, but I know that their ratio is what number to what number? 1 to 1. 1 mole of H2 will use 1 mole of Cl2. And they're both unknowns, so we can just call them X. And because both of them have a coefficient of 1, it's 1x and 1x. So we'll just write them as x. Thumbs up if you're with me so far. If this was a ratio with a 2 in front of it, I would say not x, but 2x. All right, let's write KEQ. KEQ equals HCl raised to the power of 2 divided by reactants, in this case, x times x, which amazingly enough becomes x squared. All right, so this will become HCl squared divided by x squared. Let's solve the equation for what we're looking for. What are we looking for? X. All right. So x and KEQ can switch spots because they are diagonal across an equal sign. So x squared equals HCl squared divided by KEQ. And the opposite of x squared is the square root. So what I do to one side, I do to the other. So x is equal to HCl squared divided by KEQ and square root. We know HCl is 14.5. We know KEQ is 1.8 times 10 to the 33rd.
Don't you
So-
get rid of the 2? Oh my god.
So I get rid of what 2, hon?
The 2 over HCl because it's like the square because it's your square.
Technically you could, but you still have to square root the KEQ in the denominator then, Ben. This square root would cancel out this 2, but I would be concerned about missing the square root on KEQ. So I would write it, I would write it as this is. So HCl is 1.8 times 10 to the 33rd squared. Oh goodness, I'm writing the wrong way. My apologies. 14.5 squared divided by 1.8 times 10 to the 33rd square root. All right, so we grab our calculator. I do this as 2 steps. I do this problem first, and then I hit equals, and then I do second square root, second answer on my calculator. So if I was entering this into my calculator, I would go 14.5 squared divided by 1.8 e to the 33rd, enter. And then I would go second square root, second answer. And this will give me my constant. So this is X. And X was concentration of hydrogens and concentration of chlorines. Make sure that you can do this on your calculator. One thing to be able to, so you have to be able to do a couple things. So you have to be able to write the expression, you have to be able to solve the expression algebraically, and you have to be able to make sure you can enter it into your calculator appropriately. Dejan. Let me look. All right. So record this as X equals concentration. So first off, we're the same numbers. 14.5 squared divided by 1.8 times 10 to the All right. Two significant figures. The answer is 3.4 times 10 to the negative 16th. Okay. H2 concentration equals Cl2 concentration equals 3.4 times 10 to the negative 16th. Now this has a label. What is its label? Molarity. Yes. Concentration. It would be moles per liter or molarity. Now, let's take a second and think about this for a second. Like, does this make sense? This is where the logic comes in. My calculator is a computer. It does not have a brain. I do. I can think about my answers and ask, does this make sense? KEQ was 10 to the 33rd. What direction is this reaction favoring? All the way to the product formation. Like, not a little bit, all the way to product formation. So when I talk about at equilibrium, how much of my reactants remain? Like virtually none. Right? This is 0.000000000000003. Like almost an immeasurable number will remain at KEQ. Going to form KEQ tells me that almost none. If I put hydrogen gas and chlorine gas together, it will almost completely form HCl.
No,
KEQ.
it's not good for the lab.
So KEQ tells me the relationship between product formation versus reactant formation. And so if this number is greater than 1, it means I have way more of my top number than my bottom number. And this number isn't just kind of bigger than 1, it's 10 to the 33rd
We
bigger
already
than
have
1.
it, so we already know that it's going that way. That's
Yes.
not, we're not
okay.
trying to figure out.
Yeah.
We already
Thank
know.
you, Mr. Yovko. Yeah, this is a different kind of problem because we wouldn't find K, we found concentration. All right. So there's 2 things you need to do for your homework for me and for you. This is the end of our time together discussing content from Unit 12, which means that if you haven't done the reading, you need to do the reading. If you haven't done example problems from the textbook, now would be a perfect time to do them. Your homework is to complete the equilibrium math worksheet. It's that 1 through 4, 5 through 10, and 11 through 14. Okay? That's part 1 of your homework. The solutions to this work are posted for you in Schoology. Check your work against my work. I'll show you how to do all of the problems. It's not going to help you to copy my work because I will be collecting your equilibrium math worksheet tomorrow for a grade. This one. You picked it up when you came into class.
This is homework. This is homework.
Yes.
Is this the one that you posted on Schoology?
No.
This is
You want
Packet.
these or not?
The packet, no, I don't need them turned in. The packet has answers so that you can check that you're doing it correctly. The math worksheet I will pick up for a grade. Now, all grades for basic work are due on Friday, which means if it's not done when you come into class tomorrow, I'm not going to be accepting them, right? Because we're running out of time. So please make sure you make a note wherever it is that you make notes on what to do, that you go through and you do that math. When is the test?
Wednesday.
Wednesday. The test is Wednesday. So tomorrow we will take a quiz on shifts. We will collect this. I'll answer questions and we'll work through your review, which will be the last thing that should be empty in your packet. 2 pages, Chem Equilibrium Review, and we'll begin our conversation of nuclear. Unit 13.
You learn how to make nuclear
Okay.
bombs.
Okay, all right. There you go.
Yeah.
Thank you very much.